Good evening everyone. Let us get started. So last class we discussed about state space model of a DC motor. So first we discussed what is the form of the state space model. So this is the form. First one is the x dot equal to as some function of the state matrix and the input matrix, and then output matrix is equal to as is written as a function of again state matrix and input matrix. This is the general form. And for specific case of a linear system, these functions f1 and f2 can be written as a into x plus b into u for the x dot case. X dot that is the first equation, and it can be written as y equal to c x plus du. So that means the contribution of the state matrix and the input matrix can be separated out. That is this is true for a linear system. And the elements of the matrices a b c d could be constants or could be varying with time. So in the case where it is varying with time, in that case, so those systems will be called as linear time variant system or LTV. But in the cases where the elements of the matrices a b c d are constant, that is that we can tell that that system is a linear time invariant system. So we took the case of a DC motor whose inputs were the field voltage, armature voltage, and load torque, right? And output is the speed, and states were taken as the currents like the field winding current, armature winding current, and speed. So these are the differential equations written in appropriate format to for the state space modeling. So here we could see that so actually the input or the armature current, the second equation, there exists multiplication of two states if and omega. So that case it becomes a nonlinear system, and it is not possible to write the equations in this form. So separately a b c d matrix definitions are not possible. And similar thing is true for the third equation also, where it is so if and ia, the two states appear as multiplication. Their product appears in the equation. So both these equation 2 and equation 3 are uh, nonlinear equations. But if we assume that before anything is done in the armature circuit or in the mechanical domain or mechanical subsystem, anything significant is done before that, uh, so before that the field, all the dynamics of the field circuit has settled down. So the field winding current has settled down to constant current if, which is nothing but whatever voltage, DC voltage you have applied divided by the resistance of the field winding circuit. So if we assume that, then this whole thing k into if in by La, this whole thing can be considered as a constant, and it no longer remains a nonlinear equation. Similarly, for this case also, k into if into j, this whole thing can be considered as constant, and the multiplication of two states, the nonlinearity due to that can be avoided. And if that is done, then we could write the state equation, like we could get the a b c and d matrices. So a matrix is known as the system matrix, the diagonal terms where the diagonal terms are nothing but the reciprocal of time constants of the corresponding circuit. So the first one is so the first row corresponds to field circuit, second row corresponds to armature circuit, and third row corresponds to mechanical subsystem. So the 1 element, that is the reciprocal of the time constant of the field circuit. Second 2 that is nothing but the reciprocal of the armature circuit time constant Ra by La, and third one is the reciprocal of the mechanical subsystem time constant, and whichever equation, whichever circuit subsystems do not have any coupling between the two, like field winding, if the constant if it is assumed that the field circuit has reached steady state, that is if is equal to small if equal to capital If, a DC quantity, then there is no coupling between the equation 1 and 2. So, like the state of the first equation does not impact, actually first equation, it is no longer a part of the dynamic system, because we assume that it has reached steady state. So, we understand, so it can be seen in the matrix by observing that the 1 2 and 2 2 1, those elements are equal to 0. So, this is 1 2 and this is 2 1, both these are 0, and similarly there is no coupling between equations 1 and 3, if again we assume that the field circuit has reached steady state, then If is a constant number. So, 1 and 3, so that means 3 1 or 3 1 and 1 3 both are constant numbers, but that is not true for the 2 and 3 equations. So, the state of the second equation Ia comes as torque in the third equation. So, there is a non-zero element at 2 3 there is a non-zero element, and similarly the speed of the of the of the of the third equation comes as back EMF in this equation, in the second equation. So, it basically comes as 2 3 and the previous one comes as 3 2. So, from there, so we can understand by gain insights about the system by looking at the system matrix A, and other things are B, C, D matrix. Those are uh, straightforward to obtain, and some matrix algebra can be done to come up with different control techniques in the state space using the state space model. So, that I am not going to discuss as part of this course. So, next what we started discussing about is the difference equation model. So, we have already discussed about differential equation model and state space model, which are time domain models. Next we are going to go to discrete or digital domain. So, in this case we discussed briefly in the last class that any continuous time signal, say x versus t, x is a signal and t is the time. So, any continuous time signal so what is meant by continuous time? The value of the signal is defined for all values of time. So, for all instance of time, the value of x, that is defined. But for discrete or difference equation model or discrete domain, there will be sampling done. There will be sampling done at multiple instances, and the value of the x, those will be known, those will be recorded for only the sampling instance. Like these will be the values which will be used in the, which will only be defined in the discrete form of the signal. So, x n, and this is n, where n is the sampling instance. So, these are, so whatever arrow with arrow mark, blue arrow mark I am indicating, those are like the sampling instance, and at that instant whatever is the value of the variable, continuous time variable x, that will only be held. So, in discrete time, xn is only defined for n, where n is integer number, right. It will be, say, anything 1 2 3 4, whatever you number the sampling instance, and x will be valid only for only for where n is integer numbers. So the discrete form of the signal xn is not defined for n where n is a fractional number, right? That is clear. So generally the sampling is done at a constant frequency, that is the time duration between the two, that remains constant. So this is called sampling period. Can be denoted by delta t, or sometimes it is denoted by h also, and the frequency at which sampling is done, that is sampling frequency, and this is nothing but 1 by delta t or 1 by h, and this is denoted by say fs, right? These are the uh, important terms which are typically used for which are used which are the basic terminologies for difference equation model, like sampling period, sampling frequency, etc. And also I discussed that if a continuous time signal has to be meaningfully represented in a discrete domain, like we have a sinusoid signal, we discussed we discussed in the last class that if we sample the signal at the same frequency of the frequency of the signal, then the information about the signal actually goes away. Like this is x of xt, a sinusoid at certain frequency. If we sample it at the same frequency of the sinusoid, say we sample here, then we have to sample there. So the xn should sample and hold, it will only include these values, which will appear that the signal x is a constant value. So the frequency of the variation information is lost. So even if we sample it twice the frequency of the sampling signal, say we sample here, then we sample here, then we sample here, and then we sample there, like this is twice the frequency of the previous case. So here the information about the signal which will be recorded are the green ones, right? Here the here it will be obvious that or it will be recorded that the x signal is changing its sign, but how does it change, that information is not there. So in the discrete domain, the x is only defined at these points. It could be any other points also based on the sampling instant. For an example, it could be here as well. The sampling instant could be different. That is what I am trying to tell. The sampling instant, instead of at the peak instant, it could be somewhere else also. So it could be here, 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 and here. Here also you can see that the the values held. So if sampling is carried out at this instance, then the discrete representation of the signal x will only contain the black dotted points. So but if we want to um, if we want to have meaningful information about the signal, then our sampling frequency has to be reasonably high. It should be at least say it should be at least some 5 to 10 times, at least some 10 times of the maximum frequency of the signal. So if we sample it 10 times the frequency, so this is So how many times I am sampling? 1 2 3 4 5 6 7 8 9 10 11 12. So I have sampled here 12 times. Within one period of the signal. So here you can see that the dotted points, if they are actually, if this is the representation, if this is the discrete representation of the signal, reasonably represents the nature of the signal. Yeah, it could be better if we go for higher and higher sampling frequencies, but it is reasonably good if at least it is 10 times or higher than that, right. So this is what we have discussed briefly last week also. So today we'll start with discussion about, or how a constant how a continuous time differential equations are converted or are transformed into its difference equation counterpart by using certain numerical methods. So here our I will focus on only one equation. So let us say I have the field equation. The same thing will be valid for other equations also. Right, this is the field circuit equation. So for simplicity, let me assume that Rf by Lf, that I represent as K1, and 1 by Lf I represent as K2. So our differential equation becomes minus K1 times If plus K2 times Vf. So this becomes our differential equation, which we will discretize, or which we will convert to its difference equation model by using certain numerical methods. So numerical method, uh, so in its so in essence what is done is, so this equation, this is so if we assume that If as a general state variable, say x, right. So let us start with discussion of a general form of differential equation, first order differential equation dx dt as a function of, say, x. I am taking only x, it could be x and some input u also. So for simplicity, let me illustrate the method with only x, then I will write the difference, I will derive the difference equation for the field circuit equation, where you have both the state If as well as input in the difference in the equation, right. So in the forward Euler method, what, so first one which we will be discussing is called as the forward Euler method of discretization. So here let us first try to see this graphically. So this is time. Let us let us do something. So dx dt equal to fx. Then what is x? X equal to nothing but integration of fx dx plus the initial condition, right. So x is nothing but dt. This is the time integration of fx plus the initial condition, right. This is the first and second equations are clear. So let us assume that how fx varies. Fx is basically the right hand side of the equation, right. Fx is basically the differentiation of the state variable, right. So say it varies in a certain way, in continuous time, and what we are interested in, first let me complete this. This is also t, this is say x. right? So we want to discretize, that means we have to focus on two instances. One, say, is the present instant, this is the present or kth instance, and say this is the k plus 1th instant, right? So this is known to us, say this is known to us, this is f of xk and this is f of xk plus 1, right? So at kth instant, let us say the value of x is somewhere here, so this is xk. Now in forward Euler method, what will be done is the value of fx at kth instant will be assumed to be, so between the kth instant and k plus 1th instant, whatever is the value of f at kth instant, that will be carried forward till the next sampling period. So our assumed pattern will be like this. So fx uh, between the kth and k plus 1th instant, we will assume that the value of fx remains constant at whatever is the value at xk, right? So in this case it is f of xk. So because the value of x at kth instant is known and the value of fx between k and k plus 1 is known to be a constant and equal to f of xk, then using this equation we can simply write, so integration is nothing but whatever is the area enclosed within this thing. So if we assume that this sampling duration or the sampling period is basically h, then the area is nothing but f of xk into h. So mind you, the actual area is actual area might be something different. Actual area is whatever is the area enclosed by this red curve. So this is the actual area, whatever I am trying to indicate by red hatched line, that is the actual area. But we are approximating the integration, the value of fx with the value of f xk, that is the kth instant value, and that is carried forward. So in this case the integration value is f of xk into h. So this will become f of xk into h plus x0 is nothing but xk, and this is xk plus 1. So xk plus 1 will be, because it is positive here, so it will be some value, say here this will be x of k plus 1, and it will be assumed that it increases like this, right? So if so this is what I explained, what I derived by graphically, graphical understanding. Now if I want to come to the same equation from the first case, that is dx dt equal to f of xk, f of x, then dx dt, or for all cases it will be written as xk plus 1 minus f xk divided by h, that is equal to, for forward Euler it will be x of xk, f of xk. So if you just rewrite the equation, x minus k, this h into k, so xk plus 1 is equal to xk plus h into f of xk. You can see that this is same as whatever we obtained graphically. From graphical understanding, this is the same, right? So for forward Euler, we will have to replace f of x by f of xk. This is the principle, and after that we'll have to derive the equation. So let us try to do this for the DC machine case, field equation, then it will become very clear. I'll just write dx dt is equal to fx. For forward Euler, we have to write in this way, that xk plus 1 minus xk divided by h is equal to f of xk. This is forward Euler. Now we had the DC machine field equation, that was d if dt is equal to minus k1 into if plus k2 into vf. Now what do we have to do? Simple, ifk plus 1 minus ifk divided by h is equal to k1 is a constant quantity, if is a variable, we have to replace by ifk, plus k2 is a constant number, vf is a input, so you have to replace by vfk, right? So this becomes our equation. If it is written, f of x plus ifk plus 1 is equal to ifk plus h into minus k1 into ifk plus k2 into vfk. So by using this equation, if ifk is known, like at kth instant it is known, and so at kth instant, if the current and the voltages are known, then k plus 1th instant current can be calculated. And just to remind you, when we gave the initial condition for the integrator while implementing in SIMULINK, we have to give some initial condition. So initial condition basically means, for k equal to 0, whatever initial condition value you give, that will be taken as the value of the current. So because we gave field current initial condition, the integration of that, so what I am talking about is this is vf, this was if into rf, this was integrated, okay, this was 1 by lf was done and it was integrated, and the output was if, and it was multiplied with this rf, and it was the IR drop was subtracted. So for this integration block, you had to define some initial condition. So you can see that integration block output is nothing but the field current. So once you give the initial condition, you define the initial condition, that is taken as the value of the output. In this case, it is the current, field winding current at k equal to 0, that is the starting of the simulation. The initial condition value is taken as the output, and after that, because the field voltage is defined, so from there the future values of if can be solved. So this is the most simple, this is the simplest numerical method known as forward Euler. uh, here here the known value of f xk, that is carried forward during the sampling sampling duration, and that is how integration is calculated as this rectangle area. But you can understand that there can be some errors, and actually the how fast you sample actually um, is very crucial for this method specifically. If you sample at very low sampling frequency, then it may give very weird result, and your result may be quite far off the actual result, expected result. So we'll discuss those also. Now let us go towards the next method, which is known as backward Euler. So in this case, similar to the previous case, we will discuss the graphical understanding first. So same thing we have. So let us start from equation in this case. dx dt equal to fx. Left hand side remains the same, xk plus 1 minus xk divided by h. On the right hand side, we will use the future, the k plus 1th instant values. How it will be solved, I will come to that. So in this case, this is how it will be so this is how it will be replaced. So you can see that k plus 1 appears on both sides of the equation. So it is not explicit solution. The explicit solution does not exist. That is why this method is also known as implicit. This is implicit in nature, whereas forward Euler, because k plus 1 that exists only on the left hand side, on right hand side it does not exist. So this is explicit, the solution is explicit in nature. So implicit one, yeah. So if we just write it, k plus 1 is equal to k plus h into f of k plus 1. Now it will have to be solved. It will have to be solved appropriately, and let us go to the example of decimation field later on. Let us try to understand graphically what is happening in this case. Say this is x, it is f of x, and on bottom we have x. Now f of x, we took something like this, some variation. We took some variation, say f of x varies like this with time. These were our sampling instance. So say this is k, and say this is k plus 1. So this is f of xk, and this is f of xk plus 1, right? So in this case, what will happen, we need to do the integration of fx from kth instant to k plus 1th instant. During the integration, we need to assume some value of fx. In the earlier case, we assumed the kth instant value of f of x and carried it forward. In this case, what will be done is we will take the k plus 1th instant value of fx and we will carry it backward. So we will assume that the value of fx is equal to, so fx is equal to f of xk plus 1 for or in between k and k plus 1. In between k and k plus 1, the value of fx is replaced by f of xk plus 1. So in this case, what is the area? This blue hatched area is the area, that is the integration value, and this thing, this duration is h. So the area is f of xk plus 1 into h, right? So using the integration thing. F of or basically xk plus 1 is nothing but xk plus h into f of xk plus 1. So this is the integration output, and this is the previous value. So this is the previous value, say xk. This is the integration output, so it will increase like this, increase to this, and this is xk plus 1. Now for this case, for this specific example of the signal, the red one, which is increasing in nature, you can see that in the earlier case we were actually underestimating, because the actual integration value would have been the red hatched portion, where this is the area, but we assumed it to be lower because of our assumption of forward Euler. In this case, this is our actual area, red portion, but we are actually assuming it to be higher compared to, so the actual value, if the exact thing is done, then it will be somewhere in between whatever we obtained from forward Euler or backward Euler. Now which one the prediction will be higher or lower, that depends on the nature of the signal. If it is rising, then backward Euler will predict higher and forward Euler will predict lower. But if the signal, instead of rising, it is actually falling, then you can understand that, because backward Euler will basically take the integration will be done by taking the future instant value, then actually it is lower. But if for forward Euler, this value of fx will be carried forward, so it will be higher than the actual integration output. Now let us try to derive the equation for the DC machine field using backward Euler method, which is implicit in nature. So we had dIf dt, that is equal to minus k1 into if plus k2 into vf. Right, left hand side remains the same. So if k plus 1 minus if k divided by h is equal to, what do we have to do? We have to, wherever we have some variable, we have to take the k plus 1th value. So it will become k1 if k plus 1 plus k2 vf k plus 1, right? So if this is simplified, if k plus 1 minus if k is equal to minus k1 h if k plus 1 plus k2 h vf k plus 1. Now if, there is a common term, so if k plus 1 multiplied by 1 plus k1 h is equal to if plus k2h into vf k plus 1. So if k plus 1 is equal to 1 by 1 plus k1 into h multiplied by if k plus k2 into h into vf of k plus 1, right? This is how it will be solved. We will have to use, in order to calculate if of k plus 1, we will have to know what is if of k. The future instant, because it is input, the future is also known, because we are the one who are applying the input. So even the next instant value is also known. So vf k plus 1, that will also be used, and using this equation the if k plus 1 value will be calculated. This is using backward Euler. Any question here? Okay, so let us now go to the third one, which is the trapezoidal one, which also is a implicit method. So that means on both sides we will have k plus 1 terms, right? On both sides we will have k plus 1 terms. So let us first start from mathematics. Dx dt is equal to f of x. In this case, what we will do is left hand side remains the same, xk plus 1 minus xk divided by h is equal to, we will not take either f of xk or f of xk plus 1, but we will take the average of the two. So we will take half of f of xk plus f of xk plus 1. The right hand side will be like this, right? So in this case, if it is written, it will be, so f of x of xk plus 1 will be xk plus h by 2 into f of xk plus f of xk plus 1. This is how if we solve the differential equation, if we derive the difference equation using trapezoidal method of integration, then the equation will look like this. Again, you can see that k plus 1 appears on the left hand side as well as right hand side. That is why it is called an implicit method, right? In this case, let us try to understand this graphically, what is done. So this is fx, this is time, this is time, this is x. We assume that our signal to be something like this, fx to be something like this. These were our sampling things. This is k, this is k plus 1. So this is nothing but f of xk, this is f of xk plus 1. In this case, for backward Euler, what was done? The value of xk plus 1 was carried backward. In the case of forward Euler, the value of f of xk, that was carried forward. In this case, we will take the average of the two, like the f of xk and f of xk plus 1, we will take the average of the two, and that will be assumed to be the value of fx between k and k plus 1th instance. So in this case, you can see that the actual integration output becomes to be the blue hatched area, which is nothing but h into half of f of xk plus f of xk plus 1. This is the area, and you can get this equation, like if f of xk is known, then this will be used. This is okay, this can be calculated, and this will be added to xk to obtain x of k plus 1. And actually, this trapezoidal method of integration is perfectly is exact if our fx is a linearly varying thing. If it varies linearly, then it is exact. There is, even if we are transforming our differential equation to difference equation using a approximated expression of integration, if our fx varies linearly, then it is perfect, then there is 0% error. But in case it is quadratic or higher order variation is there in fx, there will be some error, but obviously it will be lower than whatever we could obtain through forward Euler or backward Euler methods. So in this case, let us attempt to derive the equation of the field winding. So if k plus 1 minus if k divided by h. What we have to do? Our equation was minus k1 into f. So we have f, so that has to be written as half of if k plus if k plus 1. Again we had plus k2 into vf, so we have to write half of vfk plus vfk plus 1, right. In this case also it can be like, if you solve for ifk plus 1, then ifk plus 1 minus ifk, this is equal to minus k1 into h by 2 into ifk minus k1h by 2 into ifk plus 1. This is the first one, and the third, and the second part remains. There is no need to divide that. So k2h by 2 multiplied by vfk plus vfk plus 1. Now ifk plus 1, that basically appears here as well as here, so it will become 1 by 1 plus k1h by 2 and again ifk is also there here as well as here, so it will become 1 plus 1 minus k1h by 2. This will become plus, this will remain negative, so 1 minus k1h by 2 plus the entire thing k2 into h by 2 vfk plus vfk plus 1. This becomes the solution of ifk plus 1. So here you can see that kth instant if, that is the initial condition that is required, and input, the value of input at both kth instant and k plus 1th instant, both are used, right. Now let us try to see what will happen. So if we will also just go to our SIMULINK model and quickly see the impact of choosing these different numerical methods in our solution. So okay, I had kept separate space for this tree, but anyway I have derived these things there itself. So here instead what I will do is, let us say we are solving this differential equation only, Vf equal to Lf dIf dt plus Rf into If. This is the first differential equation of our DC machine that is for the field winding, right. So when we are solving it in the discrete domain, let us try to see what actually happens. Say this is x-axis is time starts at 0 and we do simulation with certain step time. So say this is the step time duration. So the simulation, the SIMULINK solves the model that you have used only at this instance. So this is the first instance, second, third. The solution is given only at this instance, and this is nothing but the step size of your simulation. This will be some this will be some time. So if you give fixed time step, then this is the step size. Now say um, I have defined my field voltage to be like this. Say this is, say our step size whatever I have taken here is 1 millisecond, right? So this is 0, this is 1 millisecond, 2, 3, 4, 5, 6, 7. Let us say I have defined Vf equal to 0 when time is less than say uh, 2.5 millisecond, when time is less than 2.5 millisecond, and it increases to say 100 volt for other cases like otherwise. So when computer actually assigns the Vf values, how it will do? At t equal to 0, we are still in this condition, we are still with this first condition, time is actually less than 2.5, so the Vf is 0. At next time step, that is 1 millisecond, time is still less than 2.5, so Vf is still 0. At 2 millisecond, still it is less than 2.5, so still it will be 0 only. Whenever time actually reaches 3, then 3 is actually higher than 2.5, so it will increase to 100 volt. So this is say 100 volt, it will increase, and it will remain at 100 volt for all the future instance of time. So it will remain at 100 volt. So mostly in MATLAB Simulink, or yeah, if you actually so generally the solution is shown to be joined. So all these points, all these actual discrete points are actually joined by straight lines, and that is why the plot appear to be like this. So they join the uh, two subsequent points by a straight line. So if you actually zoom in, the plot will look like this, but actually simulation is being done only at this instance, like 0, 1, 2, 3, 4, 5, 6, whatever milliseconds. So it depends on whatever step size you have given for your simulation. Now let us remember what was our equation of solving IF using the forward Euler method. So I will quickly write that. So using forward Euler method, IF k plus 1 was obtained by IF k plus h, that is nothing but the step size, multiplied by minus k1, that is a constant, you remember, r1 by rf by lf, that is k1 into ifk plus k2 into vfk. So this is our forward Euler equation what will be solved. Now at k equal to 0, you have initialized your output of your integration. so it is 0. So this is nothing but if, the next plot that I am trying to draw. So at first instant k equal to 0, it is defined to be 0. Now when you go to k equal to 1, k equal to 1 is if 0 plus again if 0 and vf 0. So for simplicity, let me write if1, what will be if0 plus h into minus k1 into if0 plus k2 into vf0, right? Both vf0 and if0 both are 0, so again it will be 0. When we are at 2, both if1 and vf1 both are actually 0. This is vf1, this is 0, if1, this is also 0. So this will remain like this only. When we go to if3, that is here, still if2 is equal to 0 and vf2, that is also equal to 0. So still it will remain 0 only. When we go for k equal to 4, then the value of if3 and vf3 will come up. So I will use a different color. When we go for 4, then only if3 and vf3 will have to be used, and you can see although if3 is 0, vf3 is now some positive value, so it will increase accordingly. So if will only increase here, and after that it will go on increasing, and if you look at the solution, it will be straight line joining these points, so it will appear like this, right? This is what will happen if it is solved using forward Euler. Now if the same thing is solved using backward Euler, for backward Euler, what is the equation? If k plus 1 is equal to 1 by 1 plus k1 into h, correct? 1 by k1 into h multiplied by ifk plus k2h into vfk plus 1, right? So this is our equation. The blue one is when we try to solve using backward Euler. So in this case, when we are at 0, again it remains the same. When we go to 1, again if0 is equal to 0 and vf1, so you can see that I will just write using black for any particular case, say if2 is equal to 1 by 1 plus k1h multiplied by if it is 2, it will be 1 and k2 into h into vf of 2. So for solving for 2, the value of vf which is used is the same instant 2 value only, but for if it is the previous one, that is 1. So for 1 also it will be 0, because both if0 and vf1 are 0, so this is 0. Here for 2, if1 equal to 0 and vf2 is also 0, so still it will remain here only. When we go to 3, then if2 is equal to 0, but vf3 is equal to 100 volt. So straight away it will increase from here only, and it will keep on increasing. So you can see that what is the impact of solving with forward Euler and backward Euler, or in more specifically implicit methods and explicit methods, because explicit methods they use previous instant values, previous instant input values also. So there is actually a delay between where actually the voltage starts rising and current starts rising. There is a delay between the two. But if you use implicit methods such as backward Euler or even trapezoidal, same thing, you can understand the equation is little more complicated. It is only the average of the two values. So again, when you are solving for k equal to 3, then only the input k equal to 3 will come and it will start rising from that instant only. So this is a zoomed in understanding, a zoomed in picture of what happens during this when you solve a equation using this forward Euler, backward Euler, trapezoidal methods of integration in discrete time. Now I will quickly show again, open the MATLAB SIMULINK 1, zoom in to one such waveform and show what actually happens. So I'll unshare from here. I'll unshare and I'm going to share my screen. Right, this is the DC machine model which we have seen a few classes ago, and the parameters were listed here. So I'll just focus on the step time. Step time has been taken as 1 millisecond in this case, and stop time, the simulation runs for 30 seconds. I will focus on only the field results, that is the VF, the field voltage, and IF. I will not look at other things. But within model settings, if I go to model settings, then you can see that I have set it for fixed step, and solver, if you actually zoom in, so solution time is, start time is 0 and stop time is t stop, whatever I have defined to be t stop. Now solver, which solver you are using, there are different solvers defined here. Auto is like automatic solver selection. So based on the Simulink model that you have created, Simulink will decide which solver is best for you for the solution of the system that you have made, and it will automatically choose one of these. ODE1 Euler is nothing but the forward Euler is the thing that I discussed today. ODE1BE, this is the backward Euler, right? This we will see the impact of these two. These are first order integration methods. This is another extrapolation. You can look at the help of this. This is just some extrapolation doing. So this is still a first order only. Now this ODE2, or also mentioned as when, this is a variation of the trapezoidal, not exactly trapezoidal, but a variation of that. Now ODE3, this is the third order. ODE4 Runga-Kutta, this is fourth order, fifth order, eighth order. So as you go on increasing the order, the the error basically comes down, but computation becomes more intense, like you need to calculate more. So for doing the same simulation, it will take larger amount of time. So first let us try the ODE1, that is forward Euler. Let us apply and let me solve. right. I'll only open this one. This is first one, red one is field voltage, the blue one is the field current. We'll zoom in the initial portion. We'll see the complete one. Yes. So zoom in a little bit more. Right. So this is 4 millisecond. So simulation is happening every 1 millisecond. So that means simulation is happening at 4 millisecond this instant, then 5 millisecond, 6 millisecond, 7 millisecond. This 4.5 nothing is actually happening. So you can see that your field voltage, although you have given a step, it has increased like this in a linear fashion from 4 to 5 millisecond, but it does not matter because your simulation is, or your solution is happening only at 4 millisecond and 5 millisecond, right. Now you can see that your current, when does it start to rise? It starts to rise at 5 uh, at 5 millisecond. 5 millisecond is where it starts to rise. So although voltage starts to rise here, current starts to rise 1 millisecond later on. So actually it becomes non-zero only at 6 millisecond. And you can see that this is linear between 5 and 6 millisecond, because no solution is happening between the two. The 2 points are only linearly joined. That's all. Now if I close it, go to the model settings and change the solver to ODE1BE, that is the backward Euler. Apply, okay, and if I solve it now, right, this is probably, I need to zoom in a little bit more to have the similar picture as the previous one. Yeah. So again, this is 4 millisecond, 4.5 nothing is happening, 5 millisecond, 6 millisecond, 7 millisecond. This is the these are the instance where some solution is being done. So you can see that because it is implicit method, backward Euler, so even to calculate the field current at 5 millisecond instant, the voltage value at 5 millisecond is used. That is why at this instant only it has become some positive value and it keep on rising. So you can see that in this case of backward Euler, there is actually no lag between field voltage and field current because of the solution method or the solver type utilized. So it starts to rise exactly when voltage starts to rise. So it's actually a step, because no solution is being done between the two instants, and as soon as voltage has increased, right away current starts increasing as well. So this is about uh, so I wanted to show this, the difference, that if you actually zoom in and try to understand what is happening, these solver types also matter, which solver you are employing. So you can actually look at all other solvers which are listed here. You can either search with the names given, or you can look at the help, and you will probably find some write up about all the solver types which are there in MATLAB Simulink, and you will you will get to learn about the other numerical methods which are also employed. So let us stop here today. Next day we'll discuss a little bit more about what should be the step time for when we are trying to use some numerical methods, a backward Euler, when it is stable, like about the stability of numerical methods we'll briefly discuss. So it may so happen that although your actual system is stable, because of the numerical method you are using and because of the step size, your method may go nonlinear or go unstable. You may get uh, you may get um, you may get wrong results, dramatically wrong results, because of the step size that you may choose or the numerical method that you are using to solve your system. And for certain cases we'll also discuss that which case it is better to go for backward Euler compared to forward Euler in terms of stability discussions, or uh, with stability discussion, with understanding the stability of the numerical methods, we'll understand for what type of system which method we should employ to simulate our system reasonably or accurately without incorporating any numerical errors. Okay, any question?
No, sir.
Sir, when will
Okay,
we go to control, sir? Tentatively.
uh, we will go. So after this we will discuss the stability of the numerical methods. After that we will go into the fourth way of representation of mathematical model, that or mathematical model of a system, that is the transfer function model. So transfer function model is basically frequency domain, so that we will be using for controller design. So after we reach this, probably by the next week we will be deeply into the transfer function model, and we will have the transfer function modeling of a DC motor, and from there directly we will go into control.
Okay, okay, sir.
Yeah. So after that, after we design the controllers, then again these numerical methods which we have discussed starting from the last class to today, and probably extending to the next class also, we will realize the continuous time or the frequency domain controller. If we want to implement it in the DSP, what equations we should write. We should, because of this discretization and digital implementation, it is not possible for you to write a transfer function directly. You need to write these difference equations. So this will help in that. That's all. Okay, let me stop recording.